Hello, this is Will, and today we're going to talk about Williamson ether synthesis. Now, William ether synthesis was developed by Alexander Williamson in 1850. What does it do? It forms ethers from organohalides using depronation. It's a very straightforward concept. It's a very straightforward way to form ethers. Let me show you. So here we have an organohalide right here with an alcohol group up here at the top. The first thing we need to do in a Williamson ether synthesis is to react it with this sodium hydride, or really anything that's going to donate this this H, this proton here, so that we can kick off this H over here. Deprotonating this alcohol gives us a negative oxygen. That oxygen now can be more reactive, and it can bond with this second step, which is the SN2 addition of an alkyl halide. In this case, an alkyl halide containing bromine. With this reaction, you're actually just going to stick the alkyl halide up here on the O and create a molecule such as this. This product here, and the ether is formed right here between the O, between the oxygen. Another example would be right here. We could start out with this organohalide, react it with the same sodium hydride and the same bromine alkyl halide, and you get a very similar product here. You get the substrate here, you have the deprotonated oxygen here, and then you have the remnants of the alkyl halide right here. The ether being right there. Now, this reaction can also be taken in reverse. You can also come here with a product and reason to what came before it, what was the substrate. In that example, we would actually have to take this in reverse. So we would look here and see where exactly did this alkyl halide go. You can look here and you can see that this bromine alkyl halide is actually very similar to this portion of the product right here. So then we can reason to, if that was the addition, the SN2 addition, what must have been there before? So what must have been, what the substrate must have contained before the bromine addition is a 5-carbon member, or a 5-member ring, much like this. And then you look at this O. And we know that the O is only there because it's deprotonated. This sodium hydride deprotonated this. This used to be an alcohol. So then we can just stick an alcohol right here where it would have been in the first place. And then we get the substrate that led to this product. If you want to reason it the other way back, you can also, take this and, react it with the sodium hydride, kick off the H, and then just, add a alkyl halide to the end of the O. You get the same ether right there in the middle of the structure. So let's talk about ether. Why is this reaction important? Well, it's a very straightforward and very simple way to create ether. And ether back in the day was a surgical anesthetic. Before we got into the Novocaines and things of that nature, ether was what we used to sedate or at least numb up surgical patients. Nowadays there are other lesser known reasons we use ether, lesser known reasons why we use ether. That's the main one, is it used to be a surgical anesthetic. A great article about the Williamson ether synthesis is actually an ACS. It's originally from the Journal of Combinational Chemistry. It's by Avi Weisberg, Adi Dahan, and Moshe Portnoy. It covers the reaction itself, as well as some of the mechanisms and why those mechanisms exist the way they do. That's all I have for you today on Williamson ether synthesis. I hope this was beneficial, and have a good day.